Okie dokie, folks. We're looking here at question paper 4.3, Winter 21, 0654. Okay, question 6, a physics question all about energy. So we'll get started. We've got different energy resources which are used to generate electricity, and we're asked to simply draw a circle around each energy resource. Now, this may seem fairly, each energy resource, which is non-renewable. This may seem simple, okay, but a lot of students don't look at the number of marks in the question. It's a 2-marker, so what we're expecting, without any great exceptions, is that there's going to be 2 things that you need here. Now, non-renewable resources are those things like fossil fuels, okay, which are going to run out eventually, and which also happen to be bad for the environment. And you can see 2 options there, coal and natural gas. I'm sure most people got it, but I just want to highlight the fact that looking at the marks of the question will help you kind of guide how much of an answer you're going to give here, okay? Hydroelectric, solar, tidal and wind are all renewable, so we're all good. So just check those other answers before you move on. We're then shown a geothermal power station, which is also renewable, could be useful. Okay. The cold water is heated by hot rocks to produce steam, which drives a turbine that drives a generator. Okay, so we're told here the geothermal power station can generate 0.72 kilojoules of electrical energy from 6 kilojoules of thermal energy. So what that is telling us our energy in and our energy out. Okay, not very efficient this. We're asked to calculate the efficiency. Efficiency is the ratio of the energy out, so that would be the electrical energy, to the energy in, that would be the thermal. 0.72 divided by 6, that gives us 0.12. Yeah, 12%, not great. Okay, 12% not great, but it's a good thing. Geothermal. Why? Well, we have to think about environmental concerns, okay? Not economical. You may be told, for example, that it's cheap or something like that. That's not what we're concerned with here. What we're concerned with is the fact that it does not pollute, okay? Greenhouse gases are a non-pollutant. They do not emit carbon dioxide into the atmosphere, and therefore they're good for the... did I just say greenhouse gases are good for the environment? No. I'm going to start that again. Geothermal energy does not give greenhouse gases and therefore is good for the environment. Please. That's embarrassing, but I'm going to keep it in anyway because it's fun. All right. We've done the kind of nice, easy, basic bit here, all right? Okay, now we're going to link to our electromagnetic effects. Okay, we've got a power station with a large AC generator, and we're being shown a simple one. Okay, maybe more complicated in our non-polluting, lovely, amazing geothermal power station. Okay, now we're being asked to do, I think, quite a hard thing here to define the electromotive force. Now, the electromotive force is similar to a potential difference. Potential difference is the energy which is used when 1 coulomb of charge passes through an electrical component. So that's why you get energy out of a light bulb, for example. All right. Okay. Now the EMF is the opposite. The EMF is the energy that goes into a circuit. Okay. And so therefore it is the energy supplied by, say, a battery. And when we're talking about EMF, the electromotive force, is the energy available per unit charge, per 1 coulomb of charge to go around the complete circuit. So you can imagine at the beginning of the circuit, the charge might be given 5 joules, 1 coulomb given 5 joules. That would mean it would be a voltage or an EMF of 5 volts. Okay, so just be careful when you're using the language there. Okay, all right. In the answer here, they talk about the energy supplied by a source in driving charge around a complete circuit, energy available per unit charge. Both of those would be completely valid answers. Obviously, the CIE answer is valid because they wrote it themselves. But very rarely, sometimes your answers don't quite match the answer scheme, and that's completely fine. Okay, describe how turning the coil produces an AC output. This is a tricky one, and I think it's hard, particularly for GCSE level students. The key idea about making an alternating output is the idea of cutting field lines. Between our north and our south, we've got field lines. And when that coil turns, it cuts those field lines. Okay, it cuts those field lines. Now, if you think about it this way, if you took one part of it, my field lines are being cut down, and then being cut up by each side of my my coil. And so therefore, what's happening there is we're cutting it in different directions every half turn. So if you like, the direction of cutting is linked to the fact that we're generating an alternating voltage or an alternating EMF. The idea there that they're being cut in different directions, and so therefore the generated signal is going to be changing its direction too. Okay, so what we've got here is the coil turns, it cuts the magnetic field lines. During this process, the induced current changes its direction every half turn, and that means you're going to produce alternating current. Alternating current, a wave shape, which means forwards, backwards, up, down. Okay, and so therefore different directions every half turn. I think a lot of students would struggle with that question. To be honest, I found it struggle as well to write that answer. Okay, let's try and move on, see if there's any other points to get. Okay, well, a slightly nicer question then at the end is these things here. Now these things are called slip rings. Okay, now slip rings look a lot like something called a commutator. Now a commutator is on a motor, not a generator. The commutator, just to recap, is the thing that allows the motor to keep rotating. Without the commutator, it would flip-flop backwards and forwards, and everything would get very tangled. Okay. Now in the generator, we have the slip rings. Key thing about the slip rings is as follows. One, it keeps the circuit complete. Okay, it keeps our circuit complete. If you didn't have slip rings, there would be no connection to the external circuit, and therefore you wouldn't be able to send your electricity anywhere. The main thing it does is it stops the wires from tangling. What you could have is some wires attached to the coil. Now that would still generate some electricity, but then you'd end up twisting because your generator is rotating. The wires would end up getting twisted. So at some point you have to stop the whole thing, untwist everything, and then start again. Now these slip rings, which are touched by these little carbon brushes, they just simply rotate, and they just stay in contact with the carbon brushes as they rotate round, and then therefore there's no wires that we need to untangle. There's nothing that we need to go in and fix. The generator will simply work as for a long time, as long as we're driving it. Okay. So again, I think pretty hard question this one actually. A lot about electromagnetic induction. That's a topic that a lot of students find hard. So if you're struggling with that, why not take a bit of time during your revision to kind of review those main ideas of cutting field lines, of switching every half turns, and these slip rings, which are a very small but clearly significant part of your syllabus. Okay, thank you folks for watching. If you'd like any more videos, please let me know. If you want to get instant updates, just subscribe to the channel and that will get you them popping onto your feed every time I put one up. In the meantime, all the best and all good luck with your physics revision.